Alright, hello everyone, welcome to the new section on recurrent neural net. So in the previous section, we have been spending lots of time on discussing how to handle the images as well as how to learn the representation from the images with CNN as well as how to generate the image with GAN, right? And from this section, we'll move to a new section on dealing with the text data. And in this section, we'll discuss several new models, which covers both the recurrent neural nets, LSTM, as well as this transformer and the BERT, which are the latest new models proposed in academia. So in this section, we'll first talk about the recurrent neural net and also discuss how to use this recurrent neural net to deal with sequence data like text to be discussed in this section. And here's the outline for this section. In the very beginning, we will discuss what is sequence data and how to represent a sequence data like a word. And then we can talk about the recurrent neural net, or the RN for short. And we also talk about how to use this RN for some concrete applications. And we can take the study 4 in the project as an example, how to use this recurrent neural net for classifying documents and how to use this recurrent neural net to generate some documents. And after that, we talk about a very important issue in learning the recurrent neural net, which is called gradient vanishing and exploding. And we discuss what is the cause or the main reason of this gradient vanishing and exploding in the learning process for recurrent neural nets and how to address it. And to solve this gradient vanishing and exploding problem, one of the main techniques used by now, it is called LSTM, or the non-short-term memory. This LSTM is a new neuron, right? Inside the LSTM neuron, they have very complicated architectures covering several gates as well as some other controlling modules to solve this gradient vanishing and exploding problem in the learning process. And at the end, we can briefly discuss what is called GRU, or the gated recurrent unit, which is actually a simplified version of LSTM. It can also be applied to solve this gradient vanishing and exploding problem in the recurrent units. So in the very beginning, we can talk about what is the sequence data and how to represent the words. So in the real world, we have lots of data. Actually, many of the real world data is a sequence. The main reason is because the data will be changing with time, right? So in this page, we'll show you with several examples about sequence data. The first one is about DNA or the RNA sequence. Because right now we are still within the pandemic of COVID, like if we have the COVID virus, from it we can extract some RNA sequence, right? This RNA sequence actually covers all the information about the virus. If we can decode this RNA sequence out, then we can design some vaccine, to deal with this virus, right? So for the RNA sequence, it can be represented as a chain, right? It has order among different units inside the sequence. So it can be modeled as a sequence data as well, when we apply some machine learning models to handle this kind of data. Another very classic sequence data is stock price, right? If you open your app about stock, then you can see the price of different stocks as well as this index, right? So for the stock price, we can also represent them as sequence data, right? We have a stock price which will be changing with time, and we can have the price of a long time, right? Then it can be represented as a sequence data with some orders. Besides this kind of sequence data, we can also have some other information or data which can also be represented as sequences, like a speech, right? If we say some words out, then we can record this voice. If you record your voice with some apps, actually you can see your voice, right? Which can be represented something like this, right? You can see there will be some volume as well as frequency changes, in your voice, right, over time. We can also represent the speech as a sequence data as well. In addition, for the words or the text data, we can read from textbook or from some other reading materials. All the text we read actually will be in a sequential order, right? We have words in the beginning and then the words following that. So for the documents or the words, we can also represent them as sequence data, which can cover very rich information actually. Okay, so these are common sequence data we will see in the real world. Besides them, some other data we can also represent them as sequence data as well, not a video, right? Before we mention we can deal with images, if we extend this CNN to deal with videos, we can also do that, right? Given a video which can actually cover a sequence of images or image frames, and if we have more than 24 images in a second, then our eyes will not be sensitive to differentiate different images. Then we can see this kind of images as a very smooth video instead, right? And besides videos, when we do the self-driving with data, right? We can install this data on this device at the top of the car. Then we can do a scanning of the nearby environment, which will be represented as this point cloud. We can send out some data touch, and when the data touch touches something or object, then it will be do the reflection. And this kind of reflection data will be connected and represented them as this point cloud. Because this point cloud will be changing with time, we can also represent this kind as something like an image, but it will be a 3D image, right? And it is also changing with time as a sequence. Besides, if you go to the hospital do some test, right? Do some lab test. If you do a scanning of the brain or some other organs, then we can also represent it as a sequence data, right? Because scanning process will be, layer by layer. If we do a CT scanning of the brain, then it will be something like this. We have different layers of the brain, right? Which will be returned as a sequence of images as well. Okay, so in the real world, we have lots of sequence data, and we can deal with them with the recurrent neural nets to be discussed in this section. Okay, then it comes to how can we represent this sequence data. In this section, we may be focused on the document, on the text data, right? Then we can take the document or the text data as an example in this page. So for the given document, we can represent it as a D, and we can represent its internal contents as a sequence of all of the words. Because inside the document, we have so many paragraphs, and each paragraph we also have several sentences. Inside each sentence, we also have several words or several tokens, right? So we can represent the document as a sequence of words represented as X. Inside the X, we have so many words like X1, X2, Xn, n denoting the length of this document, for example. And each X here is vector denoting one word. However, here this X is a vector, and we represent this Xi, for example, as a one hot coding of this corresponding word. What is a one-hot coding? So normally when we talk about some documents in certain language, we can always represent all the words in this language as this vocabulary set. Right? We can have one vocabulary set covering all the words in this language. Right? In this, we just show you with the example with several tokens in this vocabulary set, like man, woman, boy, girl, something like this. Right? If we have some documents, these words in this document will be selected from this vocabulary set, right? So in other words, each word here will be one word inside the set. And then depending on which word we are selecting, we can represent each word as a one-hot coding, right? As one-hot coding. So for example, if we assume this vocabulary set has like 9 different words, of course, we can have more words, right? But here we just show you with this vocabulary set with 9 words only. Then we can represent each word inside set as a one-hot coding. For example, this man can be represented as one-hot coding as 1 or the 0 for the remaining, right? Inside we have only one single entry with value 1, therefore it is called one-hot coding. Only one entry is hot, which has value 1, right? Similarly for the women, we can have 0, 1, and we have a second entry to be the hot entry, right? And all the remaining will be 0. Similar for the remaining ones. You can see in there this vector representation, the length will be 9 because this vocabulary set has 9 words. And each word will be represented as one hot coding. It will be binary. Inside it we have only one single entry with value 1. All the remaining will be zeros, right? So this is one way we can represent these words in the document with this one hot coding. You can also try to do this in your project. You can see, if we have a very large vocabulary set, then this vector will be very long, right? Because here we just show you with 9 words in this vocabulary set. If we have the real world vocabulary set for English, for Chinese, then the set will be very large with more than like several thousands of words actually, right? So in other words, each word will be represented as one hot coding. Inside we have only one entry with value 1, all the remaining like several thousand entries will all be zeros. You can see this one hot coding is very trivial, very easy. However, it will also consume more space, right? Especially if we plan to fit this data into your memory. You can see the information is very sparse. All the entry will be 0 or with only one single value will be 1, right? So this is a simple way for coding the text. And we can represent it in this way if your memory is enough, it has enough space. Because this way of coding is very trivial, also very easy for the model to learn, because inside we have only one single input which is activated as the activated input, right? So there are some other ways to coding this word input. For example, we can also represent this word with some unique IDs instead. Now here, if we have this one as a sentence input and we have one vocabulary set, inside we have 5 different tokens. Some are words, some are just some other marks. Then we can provide each word as a unique ID or index. The ID is 1, and ID is 2, dog ID is 3, this mark is ID is 4, for example. Right? If we have some word which is not included inside the vocabulary set, then we can represent this word as is out of vocabulary. Right? We also provide a widget with some unique ID like 5. And based on this kinds of unique IDs of words in the vocabulary set, given a sentence like the cat and the dog play with this mark, then we can represent the sentence as a coding like the ID is 1, right? Then we can represent the with 1 as a coding. The cat word will be out of vocabulary, then its ID will be 5, right? And same for and the dog play in example. Right? Then we can represent sentence into a coding, right? Each one represented with some IDs for the words. So you can see, compared with the previous one, this one, the input size, this input size will be much more concise, right? And because each word is represented as a unique ID. This is another way for coding the text inputs. However, this one we also have some shortcomings. The main reason is because when we serve this one as an input for the models, because when the model sees this kind of inputs, they will assume the numbers, right? Because this 5 is larger than 2, than 1, than 3, the model probably will assume that 5 will be some numbers, right? And this model will probably assume this large inputs will carry some rich information. However, these large numbers in this vocabulary set, they have no physical meaning at all. This is just one ID to differentiate different numbers, right? We can always change this ID for the words. To change this 1 to 6, it doesn't matter, right? So in other words, this value orders will create some potential problems when we fit this one into the models, because the model will assume this large number we have some potential order patterns inside text inputs. Then you can see, this 2 ways for representing text, right? This one is very trivial to handle, however, it will consume so much space, especially if this vocabulary set is very large. This one representation is very concise. However, when fitting these numbers into the models, the model will assume this large number will carry some information, right? Than the others. However, in the real world, these numbers, they have no physical meaning at all. They're just some IDs. We can always change this ID with some other values all the time, right? And to balance between them, then we can have some other representation of the words, which will be used frequently nowadays. So the way to represent words is to encode this kind of text inputs into some shorter vectors. Now here, if we have this one hard coding of the words, or we have this index representation of the words, we can always fit them into some encoding models, right? And we can fit them into some encoding models and can further represent each word as a vector, as an embedding vector, right? Now here, if we assume we have a sentence with more than 500 words, and we can represent each word as a one hard coding and fit them into the encoder inside the BERT model, right? And furthermore, we can represent each word, given the inputs, we represent them as some concise embedding vectors. Now I show you on the right. And we can represent each word as a concise vector. So in the following part, if we further plan to start some natural language processing tasks, we can just treat this kind of embedding vector as a coding for the words directly. Because this kind of embedding vector will carry all the information for the words, it can differentiate different words. However, at the same time, this embedding vector is also very concise, right? So compared with the previous two, this kind of embedding vectors, which will be much more convenient to use. It will consume much more space. At the same time, it can also differentiate different words without causing any confusing problem for the model to learn, right? Alright, so these are the sequence data we can have in the real world, as well as how to represent them, to provide the coding for them in representation.